Okay, good afternoon. My name is Srihari Pandit with Stealth Communications. I'd like to thank NANOG and its program committee for inviting us to speak today. We'll be talking about voice peering, but before we begin talking about that, we'll first talk about what's happening within the communications industry. Because of IP, we're starting seeing a lot of different vertical industries such as telecom, web, and media coming together. And they're, in essence, competing with one another for the same types of customers. So, for example, if you look at telecom, you're starting to see telecoms starting to offer video services, and you're starting to see MSOs providing voice services. Now you're seeing web companies such as Google slowly starting to offer telecom-related services embedded within the web applications. And if you look at media, if you look at Disney and ESPN, they start rolling out telecom-related services like Disney's MVNO-like services. Somewhere between the intersect between web, telecom, and media, it's creating that new communications industry, which is yet to be defined. So this is all possible due to IP technology. Service creation has really shifted towards to control of the general public. So you're no longer locked into vendors in terms of having them control what services you can potentially offer. And this allows any IT professional to develop new services quickly and rapidly. So a quick glimpse of how the PSTN kind of functions today. When a user initiates a call from one end to another, that call is traversing the TDM portion of the network. So it hits end offices and tandem switches throughout the network. Along that way, there's an SS7 network. SS7 is responsible for setting up that call and turning down that call. It also connects different types of databases, such as CNAM, LMP, LIDB, ISIP, and so forth. And these databases are required in order to be able to route a call. So for example, LMP contains information where that number has been ported to in terms of what carrier and how that call should be routed. While on the other hand, the CNAM database is responsible for storing the first and last name of a subscriber. With the introduction of voice over IP, what the initial voice IP carriers started doing in the early 90s was to replace the tandem or the IXC function by routing calls from one local market to another local market directly using IP in the middle. So a classic example of that is going to be iBasis, which is a fairly large provider around the world. And they basically can pick up a call from North America and route it over IP to some local country. And the premise behind that is to terminate calls at lower cost. Over the last 5 to 6 years, you started to see the emergence of Vonage-like companies, Vonage, Net2Phone, and Packet8. And what they decided to do was, instead of functioning as an IXC provider, why not deliver voice services to the consumer directly over IP? So in this architecture, they pick up subscribers off the public internet, routed to their SIP proxy or session border controller, and they convert that call from IP to TDM using these media gateways, which then interface to the PSTN and SS7 networks. The session border controllers, they kind of function like your routers, except in the world of SIP. So, and they also provide various security functionality. We'll be talking more about this. Where the telecommunication industry is heading towards is mashups and service delivery platforms. Mashups are just like, if you ever use YouTube and you upload a video into it, you'll notice that YouTube has a way you can embed a YouTube video right onto your own website. And so what voice mashup companies are doing is you can actually copy a couple lines of code, put it right onto your site, and now you have instant voice functionality, like click to call is an excellent example of that. Service delivery platforms is where all the telcos are heading towards right now. This is, in essence, middleware software. So if we take a look at some of these companies, let's take a look at Voxbone. Voxbone has a service delivery platform. What they do is their software interfaces with major Tier 1 operators from around the world. And through that service delivery platform, as a customer, as an end user, or as an enterprise, or as another service provider, I can electronically interface with Voxbone's service delivery platform, and I can say, hey, what's the list of your available DAD numbers? And and what's the capacity and so forth. Get these different parameters, and I can purchase those numbers on the fly using the API. And now, once I get the allocation in real time, I can then assign it to my customers. So some of their customers are Jaja, as an example. Jaja provides voice services to Yahoo. And Ribbit's another example of a service delivery platform. Jaxter is an example of a mesh-up application. Jaxter actually has voice mesh-up application that sits inside Facebook and a wide range of other social networking sites. So clearly this is where the industry is heading this type of direction. And so this is the latest in that area. The issue with this is, as voice IP continues to grow with Vonage, Net2Phone, and Packet8, and the introduction of these mesh-ups and SDPs, Calls are originating as IP, and they're going through the PSTN, and they're being converted to TDM. But on the other end, it's being converted back to IP. To make this issue even more complex, a lot of the major carriers are already in the transition to moving to NGN technology, in the sense that they're converting their core PSTN network into an IP network. So you're starting to see IP to TDM to IP to TDM to IP and so forth. A lot of replicated conversions in that process. And it's a very costly, in terms of moving calls now through the PSTN. And when your calls are initiating as IP, you have very advanced features. Like, for example, you could have HD codecs or SIP video. As soon as you route them through the PSTN, you're losing that functionality because the PSTN only carries voice. So we're aiming towards moving to an environment where our calls can be routed completely IP to IP without ever having to touch the PSTN or its SS7 elements. And so the goal is, when you initiate a call, you want to be able to route it in a peer-to-peer fashion. Just like how we have email today, I can send email directly from my mail server to your mail server without going through any middle people or brokers and so forth. And so the goal behind that is, again, to reduce costs. You want to enable advanced services like telepresence, SIP video, HD calling, and so forth. Or any new technology gets introduced, you want to be able to quickly support that. And the goal behind peering also is you want to reduce time to market, time to revenue. For a lot of carriers today, when they establish voice interconnects, especially through TDM connections, you have that provisioning interval. So if you have new applications that you need to develop, or you need to handle large amounts of call volume, like, for example, if it's political calling, or if you have American Idol-like applications, very difficult, to scale in the TDM sense. When you're an IP, if you have a gigi or 10 gigi interconnect, you can quickly scale and build SIP interconnects on the fly. So the next part of the presentation, we'll be talking about the different types of peering relationships, architectures, models, and the different routing protocols involved in routing voice over IP traffic. Just like IP peering, voice peering has bilateral peering, typically governed by commercial agreements. So these are two carriers saying, hey, I can route calls to +44 UK, and I'll send you calls to +1 for North America, and here's our route table and dial plans. We'll charge you this much, and I'll be willing to pay this much, when you send me traffic and so forth. And multilateral peering, just like IP peering, it's a sender keeps all type model. Potentially all peers peer, or they don't peer. So usually that's part of like a collective group. So an excellent example is, we'll talk about this, is the cable MSOs. They want to get together and create a group where all the MSOs can peer with one another directly for free. And this is emerging right now within the voice industry. Oops. Okay. So in terms of transport, for peering voice traffic, obviously the public internet is the common denominator there. We're starting to see slowly voice in terms of being exchanged over internet exchange points. There's special purpose-built peering platforms, distributed exchanges that carry voice traffic, and obviously private interconnects. Okay, in terms of peering architectures, we'll be talking about different methods. So the first is going to be intra-domain. So we work with a lot of carriers out in the industry. So it's kind of interesting. You would suspect that a lot of mobile operators would have actual networks tying all their local markets. So in this particular instance, this mobile carrier, when a subscriber makes a call from a New York customer to a San Francisco customer, as an example, that call is actually being transversed over the PSTN. So the first goal behind carriers implementing voice peering is they want to keep all traffic between all these subscribers on net in all different markets, whether it's in the United States, or whether it's between countries, or whether it's between different divisions. Another excellent example is, a couple months ago, a large operator here in North America just implemented ENAM now to be able to route traffic between the mobile group, the wholesale group, the retail group, and other related affiliates. And so again, the goal is to, in essence, perform a toll bypass, by moving calls over the old network in comparison to routing it over the PSTN. The issue with routing calls over the PSTN, aside from losing features, is you get hit on a per minute basis. And the second, a lot of people may not realize, is there's SS7 lookup costs, and you have to pay on a per query basis, anywhere from a fraction of a penny up to a couple of cents. And that can add up to millions of dollars for routing calls, just alone in lookup charges. The next architecture is inter-domain routing. This is where, if you look at figure number 1 up here, these are two CLECs. They want to interconnect together. This is bilateral peering. Typically, they'll have some sort of commercial agreement. And what they're doing over here is they're saying, okay, any traffic coming into this rate center, I'll take, and any traffic going to your rate center, I'll send you. And then the other type of model is obviously a transiting model, just like IP transit. You have a number of carriers selling voice transit, or they call it voice termination, to be more precise. And the advantage with this is obviously if you don't connect directly to a lot of local markets, you can transit through this particular carrier. The issue with these two models right now in the voice world is it's based on prefix-based routing. So the way a lot of carriers route today is, okay, I'm going to say plus 1212, which is New York. I want to get routed to this carrier. I want plus 202 for Washington, D.C. to get routed to this carrier and so forth. And this can be very complex and convoluted. And it's very difficult to scale. Just imagine you manually configuring your IP routers today with static routes of the whole internet. You know, the internet routing table is what, over 200,000 routes now? So in the voice world, the routing table on the PSTN is about 150,000 routes. And believe it or not, that's done on a manual basis. People manually programming static routes and switches across the entire network, very convoluted. When you go through a broker or reseller, the other issue is, unlike IP routing, where routers generally can run at line rates, the voice over IP equipment out there, session border controllers and SIP proxy servers, can only handle a couple thousand calls, and maybe some of the latest equipment out there on the market can handle tens of thousands of calls. So that could be a serious bottleneck when you route voice traffic. The other model in the telecom industry for voice is clearinghouses, and in essence, what they do is they connect all the buyers and sellers to this type of platform, and all these organizations can say, okay, I want to sell all these routes. So they basically upload their route table, all the prefixes where they want to route calls to, and then the buyers can then usually elect to pick and choose what routes they want to buy through the clearinghouse. Or the clearinghouse might say, okay, well here's our optimized prefix routing table, kind of like an internet type service, if you will. How internet takes they set B2B sessions with all the transit providers, and they come up with a magic routing table that has the best performance. So some of the clearinghouses have that type of model also. The great thing about this model is one CDR, so you get one bill. You don't get separate bills from all these different organizations. And they typically handle the interoperability. Interoperability for voice over IP traffic is still kind of not there yet. So in a sense, there's lots of different parameters. So for example, you have to negotiate codecs. You have to determine whether DTMF tones are in-band or out-of-band. And there are all these little details that have yet to be fully standardized upon. But we're heading there right now. The issue with clearinghouses is they charge commissions. So they charge you a commission on the buy, and they charge you a commission on the sell side. And some of the clearinghouses also charge, what do you call this? Credit risk insurance, which is another fee. And by the time you add up, it could range anywhere from 5% to 12% on average. In the voice wholesale industry, they're working in margins that are typically in single digits. So clearinghouses are very expensive in their business. The other issue also with this architecture is the clearinghouse is proxying all signaling and RTP traffic. So you're unable to have a true peer-to-peer type architecture. So just like how we're in this room today, we can all speak English today, and tomorrow if I want to speak Japanese or some language, as long as you can support it, I can initiate that communication with you directly. But on the other hand, if there was someone in between you and us, that person has to support that same language. Otherwise, you and I won't be able to communicate. So again, moving to a peer-to-peer architecture is definitely crucial, and that's the model of the internet. The other model is federations. Federations enable a collective of organizations to communicate on a peer-to-peer level. So in essence, what they're using is they're using the enum database. Enum is based on DNS, and we'll be talking more about this also, and it maps telephone numbers to URIs or IP addresses. So when calls are received by each of these carriers, they'll be launching a query to the enum database, and enum says, yep, route this call to this address, and then the other carrier will typically accept it. So this is set up as a multi-line arrangement. Typically, again, it's a bill and keep, so there's no fees involved or settlements. You can also use this for bilateral, but in the bilateral, different organizations have to start interacting with one another directly, negotiate a commercial arrangement, and then manually map the prefixes. In terms of peering technologies, you have static routing, which we talked about. You have enum and SRV. With static routes, this is just a very simple table how it looks. You're mapping literally, country codes and country or city codes, and sometimes even all the way down to the 7 digits. And that could be even more complex. And you're typically mapping it to your TDM group, or you're mapping it to your IP address of your SIP provider. So this is an example of an enterprise. They're typically programming their Cisco call manager or some sort of voice RP gateway or proxy server, and they're manually mapping it in. A lot of voice RP carriers are using this type of technique also. But for a lot of facility-based carriers, it has to be a little bit more advanced than just this. They have to keep track of other types of parameters, and we'll talk about that just now. So just a little background. Before the Act of 1996, the Telecom Act, telephone numbers here in North America were given out in blocks of 10,000. So it was very easy to create an LCR table because you had 10,000 block numbers, and your cost, for each of those assignments, was X, Y, or Z. But after the 96 Telecom Act, they introduced pooling resources and ported numbers. So what happened is every time a new CLEC came into a local market, they didn't want to have to open up a whole entire new CO code, block of 10,000 numbers. That would have exhausted the entire number space in the PSTN. So what they allowed to do, what they started doing is you started assigning 1,000 block numbers, and you can also start porting numbers from one carrier to another carrier, on a one-off basis. So these numbers will now be registered in the impact database or the number portability database. So now whenever you initiate a call, before you start routing on your prefix-based routing, you have to launch a query to the LNP database. And the LNP database, in essence, will return back an LRN. LRN is kind of like a location ID where you route that call to on the PSN, usually the ID of a switch in some central office. So routing in the US is quite difficult compared to any other country just because of the LNP type system. There's over 150,000 records, and you also have to distinguish between RBAC and non-RBAC. So for example, if you were to call 1-212-232-2020, which is our office number, so you know where that's going to go to. You have to check if that number's been ported or not. And then you have to check whether that's an RBAC or non-RBAC number. And there might be some other types of categories too, because your rates differ. To make that issue a little bit even more complex, if the call originated and terminated in the same state, that's one rate. If the call originated from one state and terminated in another state, that's another rate. And so you have to check the calling number that initiated the call to determine what LCR record that you want to apply to because of the cost differences. And that cost can vary by almost 1,000% intra and interstate routing. And if you have calls that are coming in from overseas, that's non-jurisdictional. That's also handled separately too, and carriers have a different set of pricing for that. Where the entire industry is heading towards is ENUM. ENUM, in essence, will map full telephone numbers, 10-digit, 15-digit numbers, and it'll directly map it to the URI. So with ENUM, you can map it to a SIP, HTTP endpoint, email addresses, HTTP. It's pretty much endless. They can support a wide range of addressing formats. The call flow for this is when a user initiates a call, it hits the carrier enterprise network. That carrier enterprise network is going to launch a DNS or enum query to the DNS server. The enum server is going to return back the NAPTR records, looks like a URL string, and some other parameters. And it'll give instructions where you can route that call to directly. So in this example, carrier 1 is going to launch a query. He's going to get the information back, and he can route it through the IP domain, whether that's a private interconnect or the public internet or some sort of switching fabric directly to the other end. That call now is moved IP to IP, end-to-end, without ever having to touch the PSTN. And through this architecture, you don't have to launch SSM queries or even query the LNP database because enum contains the exact information where to route that call to in the IP sense. So you can also use enum to do bilateral peering. We'll talk a little about that. With enum, since it's a DNS server, it's very flexible, so you can create different types of DNS views, if you will. You can also have DNS servers in each of the carrier environments. So if you have a bilateral relationship, you can set up an internal policy saying, hey, I want to check my internal enum server first, and then I want to launch a query to my bilateral peering partner, and if that fails, then launch these other queries and so forth. So you can be pretty creative about that. Earlier in the presentation, I talked about the SSM which supports CNAM and these other types of databases. And so one example is the CNAM. So whenever you receive a call, you have to query the CNAM database in the SSN network to get the first and last name, which is used to provide caller ID service. When you move that into an IP environment, those telephone numbers are not necessarily registered in the CNAM database of the PSTN because those are VOIP numbers, and voice IP carriers cannot publish their numbers in CNAM database in the PSTN because theoretically the PSTN doesn't recognize those VoIP carriers because they're not facilities based. So only the carriers that they purchase the numbers from can be recognized. So what you can do now is with enums, you can actually map the telephone number to the first and last name. So when the other party in this example receives the call, they can launch another query back into the enum database and get the first and last name of that. Enum has also been used in the mobile space. Actually, that's how MMS and SMS numbers are routed today. There's an enum database right now in the AM6 in the Netherlands, and that's how a lot of the European carriers are routing their traffic. This is how the record is stored inside the DNS server. So this is in essence the NAPTR record. So you can, associated with the telephone number, basically you're flipping the telephone number back and you're adding dots between the digits. And then the e164.thevpf.com is your DNS suffix, of the enum tree. The second line represents order and preference. These are just any numbers. So you can have a phone number mapped to multiple destinations, multiple URIs, and your the SIP proxy server or the device that initiated the enum query will then sort that information based on the order and preference. You can actually use it not only to use it as order, but you can also use it to store costing information of a particular route. There are carriers out there that are actually using enum as an LCR replacement, which is quite fascinating. And then the bottom line is the regular expressions, the URI, where you can route that call to. SRV, this is pretty cool. SRV, again, it's just like enum, except SRV is used to initiate telephone calls using email-like addresses. So just like that, every domain name, you're basically creating this type of record. You're mapping your protocol and a transport to your domain name, and you're telling what host name those calls were routed to. So in this example, any traffic for SIP UDP for StealthNet route to sip.stealth.net. So it's quite flexible. SRV really allows us to fully depart from the PSTN and remove all ties to the legacy databases and systems involved. So again, with SRV, using domain names, you can create millions of accounts, and it doesn't cost you anything. Well, on the other hand, to buy telephone numbers in the PSTN, that can cost you 20 to 25 cents per number, very costly, and that's subject to change as telephone numbers becomes more scarce. A little high-level architecture here. End users who have SIP phones or POTS phones, and you can bring them using ATA-type boxes, that typically interfaces with the application servers. Application servers are typically defined as class 4, class 5 soft switches. So there's a wide range of companies out there that manufacture these types of SIP applications, Broadsoft, Sonos. A great example is also Asterisk. It's an open source PBX system. These class 4, class 5 soft switches will typically then connect to your border element, the B. Border elements are session border controllers. They function like firewalls, and they also perform typically the routing. The session border controllers then interface to the routers, marked R in this example. And so this is the typical architecture here. The session border controllers are responsible for, in essence, hiding all the details of your internal voice network. So inside the SIP headers, there could be confidential information about your subscribers and internal topology. So a lot of carriers are deploying these SBCs in order to mask and remove all the private information before they hand the traffic off to the networks that they directly peer with. The session border controllers also have routing functionality built onto the, built right into their SBC. So they'll be performing enum lookups, SRV lookups. They also have LCR capability. Some of the session border controls also perform transcoding. So if you need to convert from one codec to another codec, for example, G711 to G723, uncompressed to compressed, they'll also perform that. Some of them also have media encryption and other types of functionality in there. Most importantly, a lot of carriers are using session border controllers as a way to perform auditing or CDR collection. Really crucial, because a lot of operators need to know how much traffic you sent me and how much traffic I sent you, because at the end of the month they can use that information to settle up with the other carriers. In North America, as an example, not sure how many of you know this, but to make a call in the US ranges anywhere from 0.2 of a penny to 0.8 of a penny. And believe it or not, carriers are still accounting those fractions of a penny. And there's billions of them a day going through the PSTN, and it's quite a nightmare collecting CDRs. So again, CDR collection is very crucial for a lot of these carriers. Some of the developments in the SBC area right now that we're starting to see over the last 1 year is a lot of carriers who have been deploying SBCs in the network have been copying their routing tables. Just like how you have routers today, there's a copy of a local routing table on each of these devices. So if, most carriers may have dozens to hundreds of these deployed all around your network. And that gets very complex because you have typically rate changes, from your suppliers or peering partners. Usually there's a rate change every 2 to 3 times a week. And once you get those rate changes in, you have to put them into your application, calculate who has the best routes, and you have to push all that routing information to all your border elements, which is marked B over here. And that's a very complex task, especially when you have 150,000 routes that have to be recalculated and repropagated out. So what a lot of SBC manufacturers have started doing is instead of locating routing intelligence right on the SBC, they're actually decentralizing out. They're ripping it out, and now they have these separate routing applications that can be centralized in your network. So when a call comes into SBC, the SBC then will, in essence, launch a query to their routing application or any routing application for that matter and get the routing information in real time to be able to figure out where to route that call to. And those distributed routing applications are typically based in enum, like from Nominum, for example. Now, the other issue right now is as people move, well, as telecom companies move into the IP domain to be able to route calls IP to IP, there's no central authority at the moment that tells you where to route all the calls to. So like in the PSTN, you have Newstore and you have Telcordia, respectively, that control all the number allocations and mapping and assignments. When you move into the IP world, they don't really apply, in that sense anymore. Now they have initiatives underway to add IP address information inside the LMP database and the LURG database and so forth. And I guess that's subject to approval and so forth, by its members. So on the internet, or not on the internet, but at least in the IP world, there's a wide range of companies offering peering services like the Voice Peering Fabric, Exonic, Newstar, VeriSign, and others. So each of these enum systems are all separate. They're not interconnected together. So this poses a problem for a lot of telecom companies. So now they have to look up in multiple enum databases to figure out if they can route that call IP. So the border elements need to be able to support multiple enum lookups. And what's crucial also is when you want to send a query to an enum database, it's not like the public internet where you can query and get the information where it's free. A lot of these enum databases, they charge you for every time you look up a number, and they may even charge you if you can make that call successfully. So when you launch queries, you want to be able to create groups and create hierarchical structures. So you want to be able to route calls to enum systems that don't charge anything first. And if those fail, then I want to launch queries to my next set of enum servers, and that could be either in parallel or in sequence. So as an example, if you have 10 free enum servers that you can query that doesn't cost you anything, you want to launch 10 queries in parallel, and that's sequentially, waiting for a response. This is an effort to reduce call setup times. Here's an example of a voice mashup company. Why is peering so important to them? So in this example, this voice mashup company, they require a number of services, 401 services. They need to get access to their MMS, SMS provider for sending out messages to mobile subscribers. And they need PSTN services. They need telephone numbers for inbound services, and they need termination capability. The issue that these organizations have is they have to provision TDM circuits. They need to purchase media gateways that convert their IP calls and convert them to TDM to send it out to their various partners. And the problem with this model is very difficult for them to scale and meet customer needs. So when they move into an IP domain, they can eliminate the need of all those media gateways. Now they can build SIP interconnects, or HTTP interconnects, or whatever it might be, with the various partners they interconnect to. So this allows them to quickly reduce time to market, time to revenue, and they can scale the business very rapidly. And this, in essence, is called trunking, or SIP trunking. You may have heard that term. SIP trunking, VoIP peering, voice peering, kind of it's all under the same umbrella, per se. It's all about interconnection. You want to be able to interconnect your voice network together in an IP environment. So it usually encompasses route discovery, transport, and a wide range of other things. Multilateral peering. So we talked about the Cable Labs MSO, Cable Labs RFP that they issued last year. And so the idea behind that is you have all these MSOs all around the United States, and there's a probability that these MSOs are sending calls, between their subscribers. So they already have interconnect agreements between each other through private interconnects or at public internet peering points. All they need to do is now have a centralized enum or SIP server that contains all the telephone numbers of all the MSOs. So now when an MSO receives a call from their subscriber, before they start sending the call to the LCR or the SSO network to figure out how to route that call, they'll prepend it all the way on the top and say, hey, I want to launch a query to the MSO enum server, and if that number's in there, then I'm going to route it directly over IP. And so for them, they're eliminating SSO lookup costs, they're eliminating PSTN costs, and they're reducing the amount of capacity needed on their TDM infrastructure to carry that voice call that would have otherwise, went on and used up that capacity. So now they can free up capacity in the TDM for other revenue generation applications. And so now once calls move into an IP environment, now they can do some really creative stuff. So they already have these advanced set-top boxes at home. They can IP enable them, put voice on them, so when a call comes in, UTV can say, hey, there's an incoming call from this subscriber. So they can do some pretty neat stuff now once calls move complete IP to IP. Why are wholesale carriers, tier 1, tier 2 operators so interested in peering? They want to use it to start eliminating TDM bilateral peering and move to IP bilateral peering. What I mean by that is they want to start moving their calls VoIP end to end. So in this example, in the voice industry, there's tons of resellers. Maybe over half the carriers out there are reselling one another. So once they move into an IP environment, they can now say, they can go directly to other carriers and say, okay, this is my rate center and these are my customers. You can send me traffic directly and you can bypass the IXC, a middleman. And by doing so, I can sell you access to my network or my subscribers at a lower cost on a per minute basis in comparison to the other guy. And all these guys are doing is, what they're doing is they're eliminating the IXC. So instead of selling the IXC at a lower rate, they can sell at a little bit higher rate below the rate that the IXC sells to the actual end customer. So they're actually reducing their operating costs and increasing the margins. So, and again, that's really key, especially where the wholesale voice industry has a single-digit margins. So the next part we're going to be talking about is some of the initiatives in the industry in terms of peering solutions and services. Okay, so we talked about Enum a lot. Originally, when Enum was developed back in 2000 approximately, it was designed to be a user or a public Enum system. It was supposed to be embedded in the Internet DNS architecture under the E164.ARPA. And there are a number of countries around the world that already have delegations in the Internet DNS servers. And I think the US is in the process, is very political climate right now. The use of these Enum servers, on the public internet, they have a little bit different application. And in essence, the model behind this is a user, just like a domain name, will purchase a telephone number, register it inside the public Enum server, and then they would be able to designate who their service provider is. It's almost like an LMP replacement. So just because a number is inside the public Enum system doesn't necessarily mean you can route that call, based on the URI that's listed in the public Enum system. So it never really took off, and it's been very slow. Now, there are some countries that are actually trying to change the way that the public or user Enum systems are designed. So what they're saying is, yeah, a user can buy that telephone number and register it, but if once that user has selected the carrier, that carrier will have to accept the call from anyone for free. And that works actually quite fascinating. And hopefully, that's where we move to. Ultimately, in order for voice therapy to really succeed, meaning in terms of being a part of the internet, like email and web, it has to be just like that same model. Where the biggest growth of Enum right now has been in private Enum systems. They're also quite often referred to as carrier or infrastructure Enum systems. They're typically systems that are operated by a collective group, like a federation or a community, or by a private entity or a clearinghouse. And they usually have a specific policy associated with that Enum system. But what's important with these private Enum systems is any numbers listed inside those Enum databases, you can route those calls directly, to the destination based on whatever NAPTR records are listed in there, unlike the public Enum systems. Okay, so in the industry, there's a number of companies providing peering services that are based on SIP and Enum. There's Spider Registry. That's, I guess, a nonprofit organization ran by NetNumber and Arbanet. Arbanet's a clearinghouse. XConnect, company based out of London. Newstar, VeriSign, and the Voice Peering Fabric. Each of these have different models, very different models. The first is the accessibility. How do you access these services? So you can access them over the public internet, you can access them at internet peering points, or they may have dedicated networks in the case of the Voice Peering Fabric. Let me put this into a little bit better context here. Okay, so these organizations, what they aim to do is to be able to help you route calls IP to IP. In order to do that, they have different types of applications. Some of them have native Enum databases where you can just query it and you can get the IP address where they route their call to directly in a peer-to-peer fashion. Some of them don't offer a native Enum access. Instead, what they offer you is a SIP application where you send a SIP invite to them, and then they'll proxy your call or send a 302 redirect message back to you, and then they'll route that call to the destination. It's kind of like, so if you look at the email analogy, if I want to send email to you, I'm going to send my email to your mail server, and then your mail server is going to determine how that's going to be routed, and then forward the mail on my behalf to you. So in essence, they're proxying the call from a signaling perspective. The RTP traffic, to the best of our knowledge, based on research that we gathered over the web, the RTP is going directly between the subscribers, between the networks that you're appearing with directly. Yeah, so signaling is proxied, and RTP is not proxied. Now the problem is quality assurance. So if you're running over the public internet, in the case that they're proxying calls, they can guarantee the signaling quality because obviously the signaling has to come in and it has to go out, so they can measure the quality attributes with it. But if they're not proxying the RTP, they cannot tell you the quality of the actual voice call. So we may have a good signaling, because we're going through this middle person, but the RTP may be going an entirely different path than our signaling. So when you're running calls through these types of architectures, you have to take into consideration how you're going to monitor the RTP traffic in terms of quality, and you have the same type of toll quality needed. Some of them also have a different type of business model in the sense they function as brokers or inter-exchange carriers. So that means they'll be buying and selling minutes with you, just like any other carrier would, except they'll take your call and route it IP, but they'll be charging on a per minute basis. Okay. And in our company, we operate a system called the voice pairing fabric, so I'll talk to you a little bit about what we've done in this area. Since the launch of the VPF in 2003, we launched the first production enum system and the first peering system for voice over IP traffic. VPF is divided into a number of categories. Well, I'll talk about that. But yeah, we've experienced phenomenal growth. Last year, we routed over 200 billion minutes. This year, we're projected to carry over 400 billion minutes. This is just a quick snapshot. On Friday, we routed 1.3 billion minutes in one day. That's approximately, on average, we'll route near from billion to billion and a half, sometimes more. The enum database is running about 250,000 calls annually, free. That's IP to IP in a peer-to-peer fashion. The voice pairing fabric is divided into a number of modules. So the foundation is we have a distributed layer 2 Ethernet network. We have pop sites in various carrier hotels, and we tie them together using wavelengths. So once you're connected into the VPF, there are two main activities organizations participate in. You have bilateral peering and multilateral peering. In bilateral peering, the VPF minutes market and ASP market allow members to buy and sell telephone numbers, outbound termination services. People in the ASP market also sell access to the SS7 network. So for example, we have a wide range of SS7 providers that connected their core SS7 networks directly into the VPF. So if you're on the VPF, you can now get access to the CNAM, LNP, LIDB databases, and a wide range of others without having to provision TDM connections, to the SS7 network. And if you want to get a connection to the SS7 network, that can range anywhere from $1,500 to $5,000 a month just by provisioning a DDS or a T1 circuit, which is outrageous. And if you're a mid-size or a large-size CLAC or an ILAC, you probably have hundreds of connections throughout your network. So this can be a very significant cost. So just the ability to descend a native SIP, a DIP into the SS7 network, or to the SS7 applications like CNAM and LNP is a huge cost saving. And by moving that into an IP environment, you're also reducing the access times. So when you query over the TDM infrastructure, typically over a DDS circuit, the round-trip delay is usually a couple hundred milliseconds. When you move it in IP, you're talking about tens of milliseconds. So the call setup times and the perceived performance when the user initiates a call is greatly improved. On the other side, on the multi-layer side, the VPF has a VPF enum and SRV database. It's a free service to all the members on the platform. The way it's used is any information you publish inside these databases, you agree to accept calls to your numbers or email addresses are free, and in return you can send and receive calls with every other organization on the platform. And this enables our organizations to be able to route calls IP to IP directly across the fabric. These are the locations where the VPF is. When we originally started deploying the VPF nodes, we looked at, first what we wanted to be able to do is focus on getting service providers, the nationals, international carriers. And they're typically located in the major carrier hotels, not the internet data centers, but buildings like 60 Hudson Street and 1 Wilshire and Napa of the Americas and, and so forth, and in London, Telehouse. And these are where all the voice infrastructure is, typically the 5ESSs or the DMS100s and so forth. And this is naturally where all the session border controllers and media gateways of all the major operators are residing in at the moment. So we basically drop in force 10 Ethernet switches in all these markets. We are provisioning wavelengths to tie all the cities together. So once a carrier is connected into the VPF of one city, they're automatically interconnected to every other organization on the platform to do bilateral or multilateral peering. And in essence, this is what the architecture of the VPF looks like. We have a BGP route server. This actually looks like a typical internet exchange point with the only exception, it's on the national, international scale. So we have a route server that collects all the routing information from all the members on the platform, and then it propagates it out. The IP addresses that are sent to the route reflector is limited to only of the voice RP infrastructure. So for example, if I'm a carrier, I'm only announcing the IP addresses of my session border controllers and SIP proxy servers and so forth, and so are all the other members. So in essence, only your voice RP traffic is traversing over the platform. It isn't very economical to route any other traffic on the platform based on the costing structure of the platform. Directly sitting on the VPF is also the enum and RSV database. The B and the R boxes represent the border element, which is the session border controller, and R represents your edge router that has BGP capability. This architecture allows traffic to be routed, from a peer-to-peer perspective at layer 3 all the way up into the layer 7, application level. So a lot of carriers are very fond of this application. VPF is not a broker, not a counterparty, doesn't function IXC, so we don't take any commissions. The business model that we have decided to pursue since the start is we just charge a flat interconnect fee to be tied into the VPF, based on the size of the connection, 10 meg, 100 meg gig or 10 gig type interfaces. In summary, what peering is all about is to be able to bring new service to market very quickly. And this is really key. What's happening in the telecom industry is a lot of legacy telcos are facing strong competition from non-traditional players. They need to be able to react very quickly against these new types of emerging companies. So if they don't move into IP, they won't be able to compete in a very rapid sense. So let's take an example. You have Google and Yahoo. They're developing applications literally every 1 hour. I see the future of telecommunications literally, it's all about applications. Telecom is going to be abstracted. It'll be all about internet access and transport. To be honest with you, that's what the future of telecom is. The next generation of what telecom companies are going to be, yet to be defined, will be all software-based because voice is now an application, just like email and web and so forth. So traditionally, voice was bundled with the POTS line, and that's no longer the case. Even TV service, even MSOs are faced with a big challenge. If you wanted to watch TV, you had to get a coax line, cable TV, in order to watch TV. With the internet, that's no longer true. You can get TV by streaming right over the website. And if you get Hulu.com as an example, and I was talking about all the industries intersecting, the media companies want to be able to deliver TV content directly to the end user any time of the day, anytime you want, so you no longer have to be fixated on the TV. And that changed the entire paradigm also, just like how Google's changing the paradigm, with advertising. The same thing applies, and the economics apply to everything else too. So in order for traditional telecom companies to be able to compete, they have to move IP to IP, and they need to be able to peer their networks with other organizations on an IP level, especially with voice traffic. And again, the goal is to remove TDM connections and to limit all these conversions because, again, you're losing features every time you're converting, and you're degrading the calls. And more importantly, it provides a very easy way to establish interconnects with other organizations very rapidly. So I hope that makes sense. And with that, I'll like to open it up with any questions from the audience. And if you have any questions, just feel free to use the mic here in the center of the room. Sorry if I spoke a little too fast. Does this make sense? I'm just curious, how many of you guys are operating voice over IP networks? Okay, and are you guys doing any type of IP interconnects for voice yet with other carriers?
Well, we buy voice that way. We also buy it over the PSTN, of course, but obviously one route is cheaper than the other. So.
So you're doing prefix-based routing.
Yeah.
Have you looked at using enum potentially as a replacement for the LCR tables?
No, we don't do that currently.
Okay. So, okay, makes sense. And you mentioned you were also doing IP too, right? VoIP?
Well,
yeah. Okay. Yeah. Yeah. Sure. Yeah, I mean, in the yeah, actually, it's a good point. A lot of the carriers that we're working with who have IP, voice over IP deployed, they have two separate networks. They have the public internet access network, which everything goes through it, and then they have a separate network just for carrying voice over IP. A lot of carriers are now not using that private voice over IP network to tie into the public internet because of the quality and security constraints. So, so that's why, like for example, the VOIP is very attractive because it's nothing to do with the public internet, but yet it's still IP and it still uses internet addressing. It's just like an exchange, like an IX. So we're starting to see a lot of CLACs and a lot of PTTs that are using a system like this to remove closed IP just to handle the quality constraints. So actually, it's interesting. A lot of the customers that we work with, when you're running multi-gigs of traffic, if you think about voice over IP, it's very small packets. So the PPS rates, packet per second rates, are very high. So that can look like a denial of service attack from some people's perspective, and that can certainly kill some routers in between you and the other party. And if you're not very well connected in terms of if you're not well peered, this is a serious issue. And in the voice industry, it's all about total quality. Business and residential consumers will not tolerate poor quality. I think if you tell them it's a mobile service, that's different because everyone's come to expect mobile service is unreliable, but they're okay with that because they get mobility. But on the other hand, if you have a fixed line service, you expect that quality to always be there. And so in essence, running direct interconnection or using a dedicated peering system like the VPF, it's almost like an insurance risk, so to speak. They don't have to worry about that. If you talk to any major wholesale carriers or any of the salespeople, they'll constantly get called. Oh, I got a blip, at 10:40 a.m. in the morning for that 3 or 4 seconds. And how do you diagnose problems like that? Very difficult, if there was a small flap here or there, and that knocks out tens of thousands of calls. So even the voice over IP doesn't use a lot of bandwidth. It creates a lot of stress in the network, and it's very sensitive to all these small, performance characteristics. Hey, Dave.
Hey, Srihari. Dave Diaz. I wasn't here. I came late, but
Oh, okay.
I was curious. What's the acceptance among the incumbents? I mean, always first movers and little guys come in, but
Mhm.
what about the SBCs, the AT&Ts? How are they switching over? Are they connecting? Are they doing, are they more or less now opening up? Are they plugging into the voice
Mhm.
peering fabric? Can you give us an update on some of the larger, slower moving fellas that are important?
Yeah. Since we launched the VPF almost 5 years ago, we support a wide range of those companies. So AT&T is certainly a customer of ours, and we service PTTs from around the world. For example, like Telecom Italia is a customer of ours, Extra Communications and Paytech. We also service a lot of the voice over IP operators like Net2Phone and Packet8, as an example. We're carrying now on average over 1 billion minutes a day of voice traffic on the platform. So we're seeing huge acceptance of moving a voice to IP in terms of moving into a VoIP format. And it's only going to continue to grow. When we launched the VPF, the first 3 years has been very fast. We saw growth rates of about 7 to 8 times per year. And now it's obviously slowed down, but the growth is still very significant. We're seeing double growth, over the last 2 years. And that's going to grow even further. Now, while we're on the subject, there's a number of announcements out there. Like if you look at British Telecom, their goal is to shut down the PSTN in the UK by 2010. And so that means they have to have the entire network all IP enabled. And to the most part, they'll be ready, I think, by then. And now we're starting to see KPN going around the same road. France Telecom and Telecom Italia, they want to start shutting down their TDM networks because it's very expensive to operate a TDM network and also a voice over IP network. So the sooner you can shut one down and move it to the other, you're going to get huge operational efficiencies also. And that allows them to quickly now start developing new types of communication applications. So I hope that answers your question.
Actually, one follow-up. How
Sure.
much traffic, if you said AT&T, for example, they're pretty big, obviously. How much traffic are they doing over the VPF? And if you can't tell us how much traffic, what size port are they handing off?
Yeah, that's a little sensitive. But I can tell you, larger customers in general do purchase multi-gigs worth of capacity on the platform, to support that. So, yeah, I'm sorry I can't get into details on that. Okay. With that, I'd like to thank you very much for your time. I'll be here to answer any other questions. And if you're interested in learning more about peering, we also organize an event about 2 times a year called the Voice Peering Forum. Our next one's on June 23rd and 24th in San Francisco. And we have over 60 organizations or 60 speakers, senior execs from all the major companies like Jaja, Reptel, Jaxter, a lot of those telco 2.0 like companies, software-based telecoms actually, that's a better term. And then we'll also have execs from France Telecom, Telco Italia, Swisscom, and a wide range of others. They'll be talking about where they are and where they're heading in the transition to a full IP environment. So certainly visit voicepeeringforum.com for more information. Again, thank you very much for your time.